Oh, like what I did right there with the 1-bar stats? Do 1-bar stats, L1, comma, L2. Yep, and then you get the whole shebang at once. It's kind of the same way you do it when you do the graph, but you have to do it in one line. Let me know if that doesn't work for you guys. Okay, here's our graph again. So we know that this is 67 inches, 68 inches, 69 inches, 70 inches, 71, 72, 73, 74, 75. Pat, I love what you said, and I want to go ahead and actually tie it in using some colors here. We know the average is just almost exactly here at 72 inches. And that's X bar right there in the middle. But you know that you can deviate from X bar. That's the idea, is you can actually deviate. That's the point. You're never at average. This is why you have to have margins of error on statistics. It's because you never land on average. You have to put the plus or minus on there to kind of track the average, as we saw with our Facebook friend data. So we go out one standard deviation to try roughly-ish 2/3. So if you go out 1.5 inches, you're going to come out to through 73 to 73.5. We'll go right to about here. And then down through 71 to 71.5, right about here. There's one standard deviation. And that's going to trap, like we said, about 2/3 of the data. Now granted, this bell curve isn't behaving perfectly because it's so small, there's not that many data points on it. As it gets larger, it starts to flesh out. We might even see some stuff appear in here. I guess depending on where I stand in class, it'd be kind of fun to see what the votes were depending on what row you're sitting in. It'd be kind of fun too. If you maybe get bigger the farther back you are, or vice versa. But what we just did was we set up 2 standard deviations. So we did X bar plus or minus 2 S's. So we've got to go all the way out to 75, and X bar all the way down to 69. So if you're envisioning a bell curve through this data, which I think is a fair assumption to make, it's missing some data points for sure. What we've just done is we've set up 2 borders. In 244 we call them critical values. You don't have to worry about that right now. But that's a fairly typical word in research too, is a critical value. It's past that, interesting stuff happens. And it might just be outliers, it might be something else, more in 244. But what we've just done is we've set up these fences that say any guesses outside those fences are unusual. Any guesses? Do we have any unusual guesses? Yeah. Yes. We've only got the one from Kels, the 67 inches, yes. That is the unusually small. Go ahead, ask me that question.
That's surprising though, because I thought 75 would be.
Now, let's come back to that. Again, Veronica, you brought up a very good point earlier. So clearly, 67 is outside of this range. It's at least 2 inches down from the lowest. So it's fairly clear, it's obvious, that 67 is an outlier. Clear. I don't think anybody's going to doubt that one. How do we feel about 75? It is the biggest data point. I love that. But how do we feel, Monica?
That it wouldn't be an outlier because there's not distance between the points.
Okay, I love what you're saying right now, because you're saying, you know what, to hell with all this analysis. 75 is right next to 74, there were 2 of those, which is right next to 73, and there were 3 of those. It's not like it's this isolated data point, it's way the hell down here on the side. That's probably, honestly, the best way to identify outliers, honestly, is to look at its relation in the graph. But if you guys want computational methods, this is one. Carly, go ahead.
I was just going to say, if the outliers are less than, or greater than X plus or minus 2S, then 75 is X bar plus or minus 2.
It is exactly that, isn't it? It's especially with our rounding it is anyway, right? Now, technically speaking, nobody's going to get in a math argument with me. Thank you, bless you all. Because I thought somebody would get in a math argument because I rounded everything up. 71.96, the actual average. Watch this bastard move. Oops, I just can't turn it off. I'm going to show you, there's a shortcut I'm about to do right now. Don't worry about it in class. It's on the quiz if you choose it for Thursday. There's a variation quiz that's got some button pushes on it to show you how to do what I'm about to do. The actual value, if I'm doing this in my head right, of X bar plus, watch what I'm doing here, 2 S's, is 74.87. So technically speaking, 75 is above that. But thank God nobody is in here going, you know what, 75 is actually above that. Good, Alan?
But isn't the graph one space so it covers from 74 to 75?
We're truncating all that to single inch increments.
Yeah.
This is mathematics to 10 decimals.
So your averaging is okay because...
It is because that number doesn't have any meaning to us, significant figures wise. What did I tell you to round to? The nearest inch. If I'm telling you around the nearest inch, I was ballsy calling that 1.5 inches over there. But the 1.45 was so close to the middle, I'm like, I think we can, much like when you're using a ruler, you can kind of ballpark where halfway between two marks is, but you really aren't allowed to ballpark any more than that. 0.87, ludicrous. Ludicrous. That's 7/8 of a, that's pointless. So thank you guys for not saying that. Very often students will go like, well, yes, but technically speaking. And you're right, technically speaking. But realistically, as you say, Alan, with the rounding accounted for, the 75 is right at the cusp. Now, real quick, I'm gonna put this back over here. And I wanna get the question from back there as well. Let me put this back, right about there, yeah? The 75 is literally at the cusp. And then the question becomes, is it equal to 75 or greater than 75? You be the judge of that one. You call it that way. I say 75 is within. I love the analysis of because it's next to the 74. I love that. It's not visibly different. It's just a predictable tail. You can see what happened if somebody guessed 76. That would then be popped out. So 75 is that nice little critical value, that nice little transition between, okay, this is where most of it is, and now we're getting a little bit weird. You don't have to have space. You don't have to have a space to have the outliers be outliers. They can be right next to each other, it's just that they've gotten too far away distance-wise. Fair enough?
From the average?
And with the standard deviations allowed for. Good? Fair-ish. Good. Another question. Marty, I think you had a question, did you? No, Carl. Did we get you?
I had a comment. Well, now I have 2 comments.
Good.
The first one was, he already said it, about the data is discrete.
It is.
So,
technically it is, isn't it?
Yeah, it's discrete data, so you can't really like
Talk about
deviate from
0.87.
point.
Right.
Yeah, because that's not really what we're measuring. And then the other thing about 75 is that when you go out to standard deviations from the average, then and you even drew those lines up, you're kind of making a fence between the typical data and the tails.
Yes.
75 is not on the tail.
Not yet, is it? It's still within the middle hump. I love both those points. We have basically forced the data to be discrete, even though it's technically a measurement, but we're not treating it as such, we're treating it as discrete points. So that kind of precision of 0.87 blah 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 is meaningless. Thank you. And you're right, that's what I was talking about Mon. Eventually the tail will begin to show up. It's clear that Kelsey's 67 is in the tail, but 75 is right before the tail begins to start. Thank you for that, perfect. Good? Let's take 5 when you come back and try to make some non-bell-shaped data. Yes! I have an idea. I got at least one idea. I got a couple of ideas actually. Yes. Yes. Yes.